Just give me a second, right? Yeah. So sorry for this delay. We'll now start the session. I was facing some network issues and everything. So because of that, the class got delayed. Just a second. Just give me a just a second. So let's start with today's session. So this is problem solving session week number 2 for this course titled as Sensor Technologies, Physics, Fabrication and Circuits. And once again, sorry for the delay. Now, so my name is Dr. Somnath Bhattacharya, and I have recently completed my PhD from IIT Jodhpur in flexible and organic electronics. And my research were towards flexible and organic transistors for neuromorphic computing applications. Previously, I have completed my master's in electronics and bachelor's in physics. So, as you all know, that the class schedule is every Tuesday from 6 to 8, and from the next class onward, it will start from 6 itself, right? So first coming to the basic course layout, we all know that this is divided into 8 different fractals, and we have already completed the first fractal of this course, that was the basics of sensors, that is introduction, basic introduction of all the like subsequent sections and everything. So we have learned a very basic about what sensors are. So let me write it down maybe. So we have already learned about what sensors are. Then we have learned about what sensors versus transducers. So what are the basic difference between a sensor and a transducer? Then we have learned about different classification of the sensors. And finally we have learned about different material choices of the sensors. And also we have learned about the very preliminary parameters of the sensors. So this was our first class, which was more of an introductory session to this course. So, after completing this one, we are moving towards the new chapter, that is the basics of sensors parameters. Now, in this, we'll learn about two different things, that is the introduction to other sensor parameters. So in the previous class we have learned about accuracy, precision of a sensor. Now we'll learn about the parameters of these sensors, and apart from that we'll also try to interpret these sensor parameters as well. Now, so one of the first just let me change the angle of this, I guess. Yeah, it looks fine. So in the previous class, what we have learned about is accuracy and these kind of things. But from now on onwards, we'll learn about the different parameters of the sensors and how to characterize these sensors to be a good fit for your specific application. So let's say a sensor has a characteristics like this. So this is our output and this is our input parameter. And this is starting from 0. Let's say it's reaching up to here, that is 100. Okay, so can anybody tell me what is the threshold of this sensor? Let's say like just a second. Let's say these everything is in psi, the unit is psi, and then what will be the threshold of this sensor? Write it in the chat box, or you can turn on your mic and say it. So what will be the threshold of this sensor? My voice is audible, right? Yes, okay. So a threshold, yeah, thank you. Now, so as I was telling this, so a threshold is a minimum signal a sensor can detect. What does that mean? That a minimum amount that that a sensor or a device can detect. So let's say you have a glass or a jug kind of a thing. So you have this, right? Now in that glass, you can see that there is a little bit of water inside this. But if there are, let's say, few drops of water, you won't be able to judge if the glass have water in it or not. So you need a very small amount of water at first. By looking by looking into the glass, you can see that if there is a water or if there is some water or not. So based on that theory, so that small amount that helps you to understand if there's water inside the glass or not, that is called a threshold amount. So in everybody has, I guess, already read about threshold. So for transistor there are threshold voltages and these things. So there are, hello. So yeah, so I guess there were some issues. Just remove this. Just a second. Yeah, sorry. So this small amount of water that can be detected by an eye is called a threshold. So threshold is a parameter that considers a very small amount of signal a sensor can detect. Now, moving on to the next parameter. So, everybody needs to understand all of the parameters, and after that, when we'll consider if a sensor is suitable for our application or not, we need to understand which parameter is most important for our use case and further, right? So, let's move on to the next parameter. So, after threshold, another parameter is called offset. So, offset is something. Um, let's discuss the definition first and then we'll move on to output of a sensor without any applied input. So what does that mean? That even if we don't give the sensor an input, it has already an output, so that is offset. Already you have a problem with the the output. So let's say a common example is like this. So you have a weighing scale which have a total, like, it's giving you something. So it have a limit of 0 to 100 kgs. Now, for this case, what happens is that, let's say the shopkeeper has already tampered with this, and it always, at the minimum point, it always gives you 2 kg extra. So even if you're, let's say you have bought some potatoes or some vegetables or something like that. So let's say your weight is 40 kgs. It will always gives you 42 kg. That is 40 plus 2 kgs. So this amount is called the offset. So let's take a look at a common characteristic of a sensor that has a offset issue. So this is our input. Let's write the input as X and the output as Y. So in this case, you can see that if the sensor is starting from this position, what is the value of offset then? This is obviously 0, right? So what is the value of offset here? Try to answer this. Two. No, no, not for this weighing scale. So this is a completely different sensor. So this is a sensor characteristics. For this weighing scale, the offset was 2 kgs, right? But for this sensor, what is the offset? The offset is nothing but 0, right? So at a point where we are not giving any x to it, so at x 0, what is the value of y? So for this case, the value of y is 0, right? So the offset value is 0. Now let's have a device like this, which is something like this, or even it meets at the same point or something. Now for this case, the problem with this device is that even at x equals to 0, the y is not equals to 0. So let's say this value as a. So if this value is a, then so the value of y is a, right? Now your offset value is a. So the a can be anything, right? So this is called, remove this a for, so this is called our offset. So at x equals to 0, the value of y is called the offset. So if the device is, let's say, um, let's say that if the device at x equals to 0 is like at the 0 point, there is no offset, and that is the optimal condition for our sensor. Now I have a question. Let's say, like, let's remove this, right? So now let's say we have a device which at x equals to 0 is y equals to 0, but at x equals to 2 it gives you y equals to 2 plus 2, something like this. So no, just write it like this. So if you have a weighing scale, okay, and when you are not putting anything on top of it, that is the condition x equals to 0, you are getting already the weight as 0 kgs. Now if you are putting a weight of 2 kg, you are getting the weight of 3 kgs. So what is the value of this offset for this condition? What is the value of this? Any others? We have got two answers. Please try to answer these questions. So we are at a very basic, like basic introductory classes and everything. So after these classes, so after 3 or 4 classes, we'll move toward more like more complex problems and everything. So if you don't answer it right now, so you will face other problems. No, so the main thing is that we already like already have discussed. So we are considering at a x0 condition. There were no offset. So the offset is obviously 0. But now, then what is the problem here? So for a 2 kg weight, we are getting a 3 kg. Why are we getting this thing? So there is no problem with offset in this case. So we don't have a offset. Offset is something that keeps on adding to the output. So at a starting point, if you have 2, after that point, even at the ending point as well, you will get plus 2 for each of the weights you are giving it. But for 2 kg, we are getting 3 kg. Then what's the problem with the machine? Last day we have already discussed about something, right? Calibration. So the calibration is something we need to do for this device. So it might be like maybe the calibration have like defaulted or something like that, so we need to recalibrate the machine and then check what is the problem with the machine. So there can be several situations. So for 2 kg it's giving 3 kg. Let's say after some time for 3 kg it will give 5 kg or something like that. So based on this change and everything, we have to recalibrate the device, the sensor. Okay. Now another sensor parameter is the range. So what is a range? That is the working region of a sensor. So what is a range? Let's have a characteristics like this, right? So this is our input, this is our output. Now our sensor has a range of this. So what is the range of this sensor? The working region of a sensor, right? Let's make it a more easier one. So for this one, let's say, what is the working region of this sensor? Try to answer this, right? Yes, the start of the curve to the end of the curve. So by this point, this is our starting point, and by this, oh sorry, and by this is our ending point. So our range is from here to here, complete. So this is our range, right? Oh, sorry. Our range is complete. So let's say this value as x1 and x2. Then the range is from x1 to x2. Okay. Now let's move on to an real life example. So this is a device that was fabricated by me. So this is a transistor. Okay. Now for this device or this characteristics curve, let me know what is the offset. For transistors, we have offset current, right? So what is the offset current? So the definition of offset current was at x equals to 0. Yeah, that's nearly the value. At x equals to 0, we need to find it out. What is the offset value? So this is our offset value. That is somewhat, so the offset is less than 1e minus 10. So we don't need to know the exact value of this transistor offset, what was the offset current or something like that, but this is the basic value. So this is our offset, right? Now, what was the range of this? Yes, 2 to 10, minus 10 voltages, and range, offset, and threshold. And what about the threshold? No, not 0 to 10. It's 2 to 10, right? Because our entire device is working from 2 to minus 10. Let's say your device is a temperature sensor and it supports a negative temperature as well. So let's say your device total range is from minus 2 to plus 2, or let's say minus 100 degree to 100 degree. So obviously a negative number can be there, right? So this is a transistor. It also can have a gate voltage at a positive or a negative voltage. So that's why the range is 2 to minus 10. Now what about the threshold? So for transistors, the offset is known as the offset current, as this is the current parameter obviously. And for this threshold, what is the value of threshold? This threshold is called as the threshold voltage, right? So what is the value of this threshold? Yeah, so right now the problem with this figure is that we are seeing this. Yeah, so there are other data points as well, you can see, right? So these are other data points. So for this specific case, we won't be able to determine the threshold voltage. You would need the proper Excel sheet of the data and everything. But the threshold voltage, as I have already told, so this is a very low threshold voltage device that is very near to 0 volts as well. So the threshold voltage we need to calculate is the difference between each points. So here you can see, I guess it's getting distorted. So the value difference between each like points is the threshold in our case. Okay. Now let's move on to the next one. So there are several different like sensor parameters. So these were some quantitative ones, but there are several parameters that are not entirely quantitative ones. So they are qualitative ones. So we have a parameter that is called the linearity parameter. So we need to know if the characteristics is linear or not. So let's say if we have a parameter like this, sorry, characteristic curve as this, right? This can be one, and this can be one. So obviously from this you can directly say that the blue one is a linear one and the red one is a non-linear one. It's very simple, right? Now for this case, let's say we have something like this. This is our input, this is our output. Okay, so you have a curve like this. These are data points. So previous data points were very in a linear or non-linear manner, but we have data points something like this. So now, is this sensor a linear or non-linear one? Is it visible, right? So this is something like this. So now, is it linear or non-linear? Linear. Okay. Others? linear. So we are looking at the trend of this line for the two answers, right? Linearity. Someone said also non-linear as well. Others? So this is a non-linear device, but if we want to use this device, we need to linearly fit this device, right? So sorry, just a second. So to fit this device, we have to fit this like this, right? So right now it looks somewhat linear. So we have to linear fit it. Now we have to determine this value. Why do we need that? So let's say at this is a temperature sensor or something like that, and this is at 50 degrees centigrade, right? At a specific point, we need to do this. So if the linear fit is x1 and this variation is up to x2, so the error is x2 minus x1, but obviously at a specific point. So at 50 degrees C, the error is this. Now, for this parameter to make it quantitative, we need to learn a parameter called non-linearity. So if sensor is non-linear, how much non-linear is it? Or how much is the non-linearity factor of this sensor? So to calculate that, the formula is somewhat like this. So we need to calculate the max change in input divided by full scale into 100%. So what do we need to do? We need to determine the maximum change in our input values and divide it by the full scale into 100%. And obviously the nonlinearity will be always within 100%, right? So is there any question about this linearity? Are there any questions about linearity? If not, then we'll move to the next parameter. Okay, that's fine. So let's move on to the next parameter. So everybody kind of knows about hysteresis. What is hysteresis? So hysteresis is when the output is altered with the direction of the input change. So what does it mean? It means something like this. We have a characteristics of a temperature sensor. Temperature sensor is our input, is our output, right? The temperature sensor somewhat behaves like this. Okay. But this is when we are increasing the heat. Okay, let's say at a point 50 degrees centigrade, this is at this, and this is at 100 degrees centigrade. Okay, so now at 50 degrees centigrade, we know just give me a second. We know that at 50 degrees centigrade, the value is this, right? Now, when we are reducing the temperature, the sensor follows a very different path from this one. So, this, let me draw it like this, but the sensor follows this path. Okay. So the main concept is that when we are increasing the input, that is the direction of the input change, we are getting a different value at a specified temperature or a specified input. So if we are talking about a temperature sensor, when we are increasing it from 0 degree to 100 degree centigrade, we are getting a different value at 50 degree centigrade. And when we are reducing it from 100 degree to 0 degree centigrade, we are getting a different, completely different value. So the concept is like this: when we are moving towards this, we are getting this, and when we are moving towards this, we are getting this. So this is called a hysteresis. So for hysteresis, we, for let's say an input value of 50 degrees centigrade, we are getting a first one that is, let's say, called as the output 1, and a second one that is output 2. So our hysteresis is output 1 minus output 2. So my question right now is this hysteresis good or bad? Do we require hysteresis or not? No. Okay. Others? Depends. Okay. Not good. Okay. Others? So why is it not good? So you are saying if there is a device that follows something like this, it is always the best device. So when it's coming back, let's say it's coming like this. So this is the best device, right? And that is the correct answer actually. So hysteresis is needed as low as possible for any kind of a device. Now, for my device, you can see that when I was giving it a positive, just a second, a negative voltage sweep, we are getting an exact same value when we are coming back. So this is a completely hysteresis free device. Let's say very low hysteresis device, right? Now, in some cases, what we can do is that, um, G. Mahesh Kumar, can you explain why it depends? Can hysteresis be good for some kind of operation or something like that? Is there any like examples or something like that where hysteresis is good, or we specifically like try to get hysteresis on our sensors or devices? Is there anything like that? You can turn on your mic and let us know. So let me answer this question. So there can be some examples where hysteresis is good, and we specifically modify our materials and the device structures and everything to get hysteresis. So take a look at this example. This is my paper that is published in Wiley Advanced Materials Technology, where we are specifically trying to get a transistor with hysteresis. So how does we know that it has a hysteresis? So in the previous example, we can see when we are giving it a negative and positive bias, there is no hysteresis after 0 volts. So this is a complete hysteresis free device. But now you can see that when, sorry, just a second, yeah. So when we are, just a second, sorry. So when we are giving it from a negative, sorry, just, yeah. So when we are giving it a negative voltage bias and a voltage sweep, we are getting these kind of a curve, right? That is a normal transistor curve. But when we are coming back from this negative to positive one, we are getting a curve something like this. So the device completely behaves something like this. So the device is going towards this, a normal transistor behavior. But when we are coming back, the device is giving something like this. So that is not a entirely complete transistor behavior. So what happens in this case is that we are trying to get a higher hysteresis device. And why do we need it? For memory purposes. So like if we need to have a memory that stores data, so we need hysteresis, right? So this is our hysteresis window, or also known as the memory window here. So as I was saying, just let me use maybe black. So when we are going towards this, there is a complete transitive behavior. But when we are coming back from this, when we are coming back from this is the high hysteresis behavior for these devices. Now let's say for a certain volts, let's say at 2.5 volts, right? If we extend this curve, we have it here and we have it here. So there's a hysteresis window forming at, let's say, 0 degrees, 0 volts. There's a highest hysteresis forming. So the hysteresis is also programmable based on the voltage you give it. So if you are giving very low voltage, that is 0 volts or something like that, apart from the polarity of the voltage itself, so the hysteresis is very high. But when you are giving it a very high voltage, that is 2.5 volts or negative 2.5 volt, based on the device polarity and everything, so you will get a low hysteresis. But by changing this, you can control this behavior, and utilizing that you can make a memory that is, when VGS is getting towards a higher point, that is the zeroth state, because no memory is stored there. But when VGS is coming back from a higher value, that is -5 to a +5, so it gets to a state that is called the one state. So this one is a one state and this is called a zero state. So thus a non-volatile memory OFET or a non-volatile memory transistor is being made now. So this is being used for memory behavior or non-volatile memory behavior, right? Now in some cases, let's say for sensors, hysteresis is completely undesirable, right? We don't need any kind of a hysteresis in sensor behaviors. But there are several cases where, like this memory behavior, we say hysteresis is a desirable behavior, right? It is desirable. So based on your use case, based on your different needs, you will need to have these different parameters in a different ways. So for these memory transistors, so just a transistor with a hysteresis can work as a memory. So by this you can say that in these cases hysteresis was an internet property and it was desirable, right? Now moving on to the next one. So these are several other parameters as well. So selectivity and repeatability. Now, selectivity is that how selective a sensor is towards the target parameter. So anyone knows about selectivity? What is selectivity and what is not? Any basic example of selectivity as well. So like if you can give a basic example of a selective device. Enzymes. Yeah. Sensor for detecting enzymes and all. Sensors for detecting something, like here we have gotten specific example of enzymes. Similarly, something like gas sensors. These are one of the most common sensors. So let's say we have a gas sensor that can detect NH3, N2, and H2S. Okay, so we have three different kinds of gas. So the gas sensor should be selective. Why it needs to be selective? So let's say if a gas sensor is selective, is not very selective, what it can do is that while like looking for a NH3 gas, that is ammonia gas, it's also like getting activated by nitrogen in common air. So it will be a faulty device, right? So we need a completely selective device which can detect only a single parameter and not the other parameters. So then we would say that this is the NH3 sensor, right? Now, what is repeatability? Any idea? What is repeatability? Yeah. Then what's the difference between repeatable sensor and a precise sensor? So what's the difference between these two? So as per the definition, right? We know that a sensor that is completely repeatable, like smallest change. No, that is not a precise sensor. That is accurate sensor. So in the previous class, I'm not sure if you have joined in the previous class, but in the previous class we have already discussed about an accurate sensor and precision sensor. So how does a accurate sensor and a precision sensor differs in operation? So now I am asking about what is the basic difference. So a repeatable sensor is something like let's have an example, right? So let's say you have a NH3 sensor, right? The previous NH3 sensor, and for the first few cycles it's getting like 2 ppm, 2 ppm, 2 ppm, something like this is a completely repeatable sensor, right? We can repeat the results. So now my question is difference between a repeatable sensor and precise sensor. What is the basic difference between these? So what is the basic difference between these two? What is the basic difference between these two? So a repeatable sensor in presence of variability will. I didn't get your answer. Can you repeat it again? Oh, variability will be there. Yes. So about that, what does that variability? So which one is a good sensor, repeatable or a precise sensor? So, what the main thing is that a repeatable sensor, no, that's not a correct answer, not a repeatable sensor. Because let's say, yes, precise sensor will be always good because in the same conditions, environment, temperature. Yeah, so what I was saying that let's say we have something like this, right? So for a repeatable sensor, let's say we are measuring 10 degrees centigrade, okay? And let's say we are getting a 7 degree centigrade value. So for each of the iterations, we will be getting this 7 degree centigrade, and this is called a repeatable sensor, right? But for a precise sensor, the main thing is that how precise is it? So for let's say 10 degrees centigrade, we are getting a value that is 9 degrees centigrade. Somewhere we are getting 11 degrees centigrade. Somewhere we are getting 10.2 degrees centigrade. So this is a very precise sensor, right? It is not a repeatable sensor. It won't be able to repeat the answers. But for a precise sensor, the answer don't need to be repeated, but the answer needs to be precise. Now let me know which one is like complete, like which one is a more desirable sensor. Which one do you desire for your specific application? Does it need to be repeated? No, because there's an error of 3 degrees centigrade for the repeatable sensor, right? But for the precise sensor, the error is only zero point 0.2. This is a very precise sensor that is not repeating, that is not accurate at all. So in any of the cases it is not giving 10 degrees centigrade. So the precise sensor is not that good, and repeatable sensor is obviously not that good because it's anyways giving 7 degrees centigrade. So it already is repeatable, but the problem with this sensor is that it will always give 7 degrees centigrade. So even if you like let's say increase the number of data points, that is for 100 times you are measuring that 10 degrees centigrade, you will always get that 7 degrees centigrade or some nearby data. So the problem with these sensors are that we will be getting 7 degrees centigrade. So the basic difference between the actual and the measured value will always be 3 degrees centigrade. But for a precise sensor, if you are constantly increasing the number of iterations or the number of data points you are collecting, you will move towards more preciseness. So that is for 10 degrees centigrade, let's say for 10 iterations it will give a error of zero point 0.1 degree centigrade. But if you are moving towards more and more and more number of data points, it will move towards the actual, and the actual and the measured value will be exactly same. So this is called a precise sensor, right? Now, apart from that, we also have a method to calculate the selectivity of the sensor. So how to calculate this selectivity? For let's say for a parameter 1, for the first parameter we are getting a value x1, right? For a second parameter we are getting a value that is x2. So what is the error between them? That is mod of x2 minus x1, right? Whichever is higher it will be at first. So the selectivity values will be nothing but del by the full scale multiplied by 100%. So what is the selectivity of that sensor? You will get to know, right? Now let's move on to the next one, that is called a dead band. So what is a dead band? Just let me draw it. So a sensor that has a characteristics something like this, right? So here, let's say the device starts at 10 degrees centigrade. This is our input, this is our output. And at 50 degrees centigrade, the device is like this. And at 100 degrees centigrade, the device is like this. But and this completes at let's say 200 degrees centigrade, right? So what is the dead band? The dead band is an region where the sensor is completely insensitive. So this is called a dead band. Within this region, the sensor is not actively like detecting the parameter, right? So now our deadband is obviously 50 degrees C to 100 degrees C. So what does this mean? That with change in x, with change in x, there is no change in y. Now, so what is the span of this device? So what is the span of this device or range of this device? What is the range of this device? 10 to 200. Obviously, in the device, this is 10 to 200. No, don't consider it as like this, right? The I have drawn it like this, but the plot is something like this, right? So it is 10 to 200 degree, obviously. The range is 10 to 200 degrees centigrade, and our deadband is from 50 to 100 degrees centigrade, right? So for a specific use case where you don't need to like measure the value of a temperature range from 50 to 100, let's say your machine will be at a specific range that is less than 50, like let's say 40, 45, something like this. And in that machine itself, you have another part that is at this range 100 to 200 degrees centigrade. So you can use the sensor specifically for that use case, right? Now, moving to resolution. So what is the resolution? Resolution is the smallest amount of detectable change a sensor is able to detect. So what does that mean? So let's say we have a temperature sensor that is moving from 50 degree to 51 degrees centigrade, right? Now in this case, let's say that the value is 20 millivolts, the change in voltage, right? And for 51, let's say the value is 22 millivolts. So what is our resolution? What is our resolution? One. So we are not entirely talking about 1, but this is less than 1 degree. So resolution is less than 1, right? No, not 2 millivolts. The resolution is the amount of smallest detectable change. So always resolution will be in terms of the input values, right? So our input was this, our output values were this. So based on this, the resolution was less than 1. Now, let's say if the device was something like this. So at 50.1 degree centigrade, the value is 20 millivolt. At 50.2 degrees centigrade, the value is 20.2 millivolts. So what is our resolution? So for this case, what is our resolution? No. So which one is it correct? Point 2 or point 1? Obviously not. It is point 0.2 degrees centigrade. Why is it point 0.2? Because at 50 it was 20 millivolts. At 50.1 it is 20 millivolts. So for a 1.1 degree change in our input, there is no change in our output, right? But when we are changing it to zero point 0.2 degrees centigrade, the output is changing by zero point 0.2 millivolts. So obviously this is our resolution, right? So this will be zero point 0.2. The value will be zero point 0.2. Now Moving on to the next one, what is stability? What is the stability of a parameter? Sorry, for a sensor. How stable a sensor is, right? So if let's say you have a sensor which has a characteristics like this, right? Now by changing the environmental factors near it, the sensor is working like this. And we have another sensor that is decaying a bit, right? So which is the most stable sensor in among these? Obviously the purple one, right? This is a stable sensor and this is a not so stable sensor, right? So what can be different parameters that makes this sensor stable? So it can be either mechanical. So based on mechanical force, let's say you have a flexible device and based on this mechanical force, if the sensor is stable or not. We can talk about chemical profile. So like if the sensors are chemically stable or not. We can talk about if the sensor is environmentally stable or not. So the stability is that the change or the variation in the characteristic, like the characteristic of this device based on change in your environment, that is the environment chemical status or the mechanical status. So this is called how stable is a sensor. Now apart from this parameters, we also have some separate parameters, that is like few fluctuations based on electrical device and these kind of things. So these are called the noise, that are this unwanted fluctuations. So how can like a sensor like have noise? So it can have noise from itself. So if the sensor has fewer problems with the fabrication steps or something like that, it can like have noise itself. So let's say if a sensor has a output like this, but it's showing something like this, a fluttery kind of a behavior. So it is a noise that is also known as the flutter noise. So there are several different kinds of noises as well. So there can be flutter noise, there can be some other noises as well. Now another thing it can get noise from is neighboring sensors or circuits. So if you have neighboring sensors, let's say something like this. So if this sensor is working, this sensor will always have some noise. So let's say it the intended output was something like S, it will always have some noise. So from the neighboring sensor or circuit, you will have some noise, right? Another possible cause of this noise is its own. I want to know how many particles of NH3 is present there. So in the first case it gives 2, while in the second case it gives 3 only. So it is not a repeatable sensor. A sensor should be repeatable in any case, so it should give always 2. It's a very highly repeatable sensor, and we want a very highly repeatable sensor and also a very highly selective sensor in case of biological cases or gas sensing kind of a thing, or even like chemical chemical sensors. It should be a very highly selective sensor and also a highly repeatable sensor as well. Now uh, oh oops, sorry, just a second, we missed a part. Yeah, so the value of just wait a second. The value of repeatability is characterized as the change in del divided by the full scale value into 100%. And what is del? Del is the change in the value. Just wait a second. If for the first case we are measuring and we are getting an characteristic of like this. So for a value of x1, we get a value of y. In the second case, similarly, we have measured another characteristics where for the same value of y we get the value of x2. So here the del, that is the deviation of the input value, that is, it is the value of x1 minus x2. So this is how we measured the value of repeatability. Now the next topic is deadband. A sensor becomes insensitive within a certain amount of range. It can be within the like, what do I say, within the range itself, the working region, or it can be outside the working region as well. So if a sensor is performing like this, while going towards this, it becomes saturated for a certain amount of time, then again it starts working. So within this amount of time, let's say this is x, this is y. Y is our output value, while x is the input value. So if the values are from, let's say, 10 to 250 degrees centigrade, for a temperature sensor, a temperature sensor has a working region of 10 to 250 degrees centigrade. And in between there is a certain range that can be anything, like for a different sensor it can be different values, but let's say from 50 to 100 degrees C, there is no change in the output value. Even if you even if you change the values after just 100, it starts responding again. So we can say within this working range there is a deadband of, there is a single deadband. There can be multiple deadbands as well. So like a sensor can work like this even. So in there can be two deadbands as well, but in this case we have a single deadband which is from 50 to 100 degrees C. So in a worksheet, you should always mention that your fabricated sensor is working within within the range of 10 degree to 250 degree centigrade, and in between there is a certain range of a dead band which is where that sensor is insensitive to any kind of a change in the input values, that is from 50 degree to 100 degree centigrade. Yeah. So the next parameter is resolution. Resolution is one of the most important parameters for an sensor. A smallest amount of detectable change a sensor is able to detect. That is, if the sensor can detect 50 degrees centigrade and it can detect 51 degrees centigrade. So the resolution in this case is not 1 degree centigrade. It can be also less than 1 degree centigrade, but it's not greater than 1 degree centigrade. So what happens if we are getting values for, like, let's say at 50 degree centigrade we got a value of 20 millivolts. In 51 degree centigrade we got a value of 22 millivolts. So there can be a certain value that like 50 sorry 50.2 degree centigrade, the value is 20.2 millivolt. So there's a certain change in the value, that is zero point 0.2 millivolt change. So the resolution in this case will be 0.2. We have to go much lower in the values. There can be a certain case like 50.1 degrees centigrade, there is no change, that is, it's showing 20 millivolt in the sensor, so it doesn't have a resolution of 0.1. So the resolution will be, in this case, will be equals to 0.2 degrees centigrade. So this is one of the most important parameters for a sensor. While we are characterizing a sensor, this is the most important parameter, that how much resolution your sensor have, how much a small change can it detect. Like in many cases we tend to have a sensor with higher kind of a resolution. So if there is a very sensitive case that we have to maintain a temperature of let's say 270 degrees centigrade for a specific material, even if there's a slight change of like 272 degrees centigrade, the material will corrode. So what will happen? So we need a temperature sensor which can detect at least a 1 degree C change. The resolution of the temperature sensor should be 1 degree C. So that's why we get to know whenever it's reaching to 271 degrees centigrade, we'll get to know and will then reduce the temperature in that furnace or something. Now the next topic is stability. Stability of a sensor is like how stable is your sensor. So let me say that if a sensor, wait a second, let's see, if a sensor have a characteristic of like this is the input values and this is the output value. So if a sensor is like this, in any kind of a condition, it should the characteristic should remain like this. So now if let's say if it is an organic sensor, so in case of organic materials, we know most of the organic materials are have an issue with relative humidity. So what happens that these kind of materials soak the air, like soak the water from the humid air, and it changes the performance. So this is a kind of a environmental stability. If the sensor doesn't change its track, like the characteristic can be slightly different, but it stays kind of a same. So we can say that this like this sensor is environmentally stable. Similarly, there can be mechanical stability for flexible or wearable sensors in our watches, smart watches or some kind of thing, or smart bands. There the sensor should be flexible, so whenever we bend the sensor, it should not break down, it should remain the exact same kind of a characteristics after multiple times of bending and multiple times of usage. There can be like there is mechanical, there always can be a chemical sensor. In case of like underwater sensors or something like that, what will happen that the water will seep down inside that sensor, and it will change the characteristics. So like underwater sensor or a sensor which is like very nearby to a chemical substance, it should be chemically stable as well. Other than that, there can be environmental stability, like in case of wearable sensors. So these are different kind of stability. In terms of the specific application, the stability changes for each sensors. Yeah. So noise is another kind of a sensor parameter. A sensor parameter can have noise from within itself, or it can have noise from the like near like we can say neighbor sensors as well, neighbor sensors or circuits, and also from its own interfacing circuits as well. So there can be the noise from itself. There can be several factors, like a change in humidity can change the characteristic. It can be said as an humidity noise, or due to humidity there is a new noise present in the system. There can be noise from the nearby circuits or sensors, like if there is your sensor and it is fixed in an array. So what will happen if you are characterizing this sensor, the nearby sensor can affect that, and due to the noise from this sensor is also in a working state. So what will happen, the characteristic of this sensor will change. If the characteristic was like this, it can change to like, it can maybe saturate or something like that. And also its own interfacing circuit, the interfacing circuit is a very important part. This is where the sensor is connected to your main what do I say, the main instrumentation. There is certain interfacing circuits always, like in a piezoelectric sensor where you press the material and it gives a certain amount of voltage. The voltage amount for an organic material is very low, like in even like millivolt range. So you should need an amplifier to amplify that values, and use it in use in like usual cases like that. So what will happen that the transistor can have like noise itself. Because of that, the value of the piezoelectric sensor will change, and it will induce noises in the signal as well. The next one is excitation. In case of active sensors, we need an external power supply, that is the external signal. It can be a voltage signal or it can be a current signal. In case of like transistor type of things, we need an external signal anyways because it's an active sensor. In case of like MOSFET based sensors, we need this kind of an excitation, but it is only needed only for the active sensors that you have to take in consideration. So now we'll look into like several like transient parameters. Like throughout the previous slides we were talking about the like the parameters even when there is a no change in the time, but time is also an important factor which we have to take into account. So a sensor has a response time. What is a response time? Let's say if we have an photodetector, so what will happen, let's say a photodetector has a characteristic like this. So if we are giving an light, we get a voltage value. This is a very simple characteristic, very simple normal characteristic. But in case of like time dependent variation, when you turn on a light, the light can be like this light value. What will the sensor do? It will increase the value at a certain point, and after that point it will start decreasing. So there's a certain delay you can see. Sorry, it should be like this. And so with respect to time, the value of voltage changes. Let's say this region is when the light is on, whereas this region the light was off. So what happens in this case, that whenever the light is shined on that photodetector, the photodetector starts generating, just a second, yeah, the the photodetector starts working, but to reach at least 90% of the maximum value, it takes some time. So this time, there's a certain time to respond. We can say the 90% of the maximum output, the sensor takes a certain amount of time. Let's say it can be like 5 seconds. A 5 second is a very bad number for an like photodetector or some kind of a sensor, but let's say it's 5 seconds. A sensor takes at least 5 seconds to reach the let's say it is A1, so zero point 0.9 A1, reach the value of 0.9 A1. It takes about 5 seconds, so the response time will be here 5 seconds. The response time should be as low as possible, like in the nanosecond range, or even like even in some cases we can have a sensor with microsecond ranges, but this should be as low as possible. Whereas the recovery time is a different kind of a thing. Like if we draw this similarly, we have a light pulse that is off, on and off. This is the voltage axis and this is the time axis. So what happens, the detector starts working here, and after a certain time when the light is turned off, that without any applied input, the the value of the voltage, that the value of the output starts decaying. When the value of this reaches the value of 10% of the maximum output value, we say this value is the recovery time. A sensor should always work like this. If the input value is like this, the sensor should work like this, or with a certain amount of delay like this maybe, and like this. Always a sensor should work like this. So the recovery time should be very less, in nanosecond preferably, and the response time should be very low, that is in the nanosecond as well. So let's move on to some questions maybe. So based on the details I have already told and also from the lectures, what should be the answer of this? The variation in the constant of proportionality between input physical quantity with output electrical signal. What is the what is the term? Oh, sorry, I may have missed the term. Just wait a second. Yeah. So drift, about drift, I forgot to mention. Sorry. Drift is in characteristics of a sensor. If the sensor for let's say for 50 degrees centigrade, and temperature sensor should give 20 millivolts of value. So let's say the value is here. When we are giving in 50 degrees centigrade, the 20 millivolt should be here. So even after like several hours or something, the value should be here. In real case it should be here, but most of the sensors starts decaying after some time. So this is the drift of the real response. With respect to time, there is a change in the output value. That is the drift in the output value. So it's characterized as the drift. So now answer the question. Maybe you can also type in the chat box as well. Just give me a minute. Yeah, everybody can hear me, right? Linearity. So can you explain the others? Like I need some responses. So like why it's linearity? Why is it not hysteresis or repeatability with like within a single line or something? Maybe you can write down as well. Any one of you. Why do you think like linearity is the proportion between the physical quantity and the electrical signal? The answer is linearity, but like I need a descriptive answer, not the exact like why is it linearity? I have told about the drift. Let me maybe explain here everything. Hysteresis is what? With the direction of input value change, change in output. Okay, so this is not the change in output, and this is also not the change in output with respect to time, that is a drift. Repeatability is obviously not this, because a sensor should be repeatable for this case. If we are going from this point, the sensor should every time go from this point. The value, the answer is linearity, because like it's the proportion between the physical quantity with respect to the electrical signal given to it. Let's move on to the second question. Yeah. Change in output with respect to change in input. What is it? Yes. Can you please explain this? Because like I want someone to answer me, as it is a live interaction session. So like through the chat it's fine, but if someone can answer me, and then I can ask him some questions, him or her some questions. Yeah, it's sensitivity. Let's move on to the next. Hmm. So in case of a temperature sensor, for temperature value of T degrees C, we have a resistance value of R ohm. So the equation is R equals to 4.7 T plus 6. How to get the value of sensitivity in this case? Yes. Why is that? Yes. Slope. That is, we need dr by dt. Change in resistance with respect to change in temperature. That is del output by del input. The value is nothing but 4.7. Yes. In kind of a similar kind of a case for a pressure sensor, this is the equation. What is the value of offset present in the sensor reading? Others? Others are getting the like getting these things or not? Like apart from Sonakia and Murugation. Let's take about 1 minute maybe. other than these two? Any idea how to like get the values? So in the previous case, what we have done, we had got the value of sensitivity, right? So sensitivity was what? Change in the output value with respect to change in the input value. In this case, what will happen? We get dr dp equals to 12p plus 7. So the value we have calculated it was wrong anyways. Even the sensitivity will be 12p plus 7. We need to get the value of the input pressure at least to get the sensitivity. So the value will be dependent on the sensitivity itself. Oops, sorry. With respect to change in the pressure, if the pressure is P1, that can be like 1 maybe. So the sensitivity will be 12 plus 7. Whereas if we are calculating for this value P2, P2 can be maybe 2. The value of sensitivity will change. Sensitivity for P1, sensitivity for P2. The value will change. In this case, the value will be 24 plus 7. So it's dependent on the input value as well. The sensitivity depends on the input value. But what will be the offset value? From what I have done through this modification, maybe you can do that right now. What will be the value of the offset? Let me do it. So what will happen in this case? Offset is the value of y, that is the output, when the value of x or input is 0. So in this case, the input parameter was P or the pressure. So we have to calculate the value of output at P equals to 0. So in this case, what will happen? Resistance R equals to 6 into P square plus 7 into P plus 4. So the value of offset will be, that is R offset, or we can say R at P0 is nothing but 4 ohms. Oh, okay. So in the previous case as well, So what we have done, it was a bit wrong, because like we have to always put the units in this case. So what will be the unit of this? Sorry, I missed it. What will be the unit of this case? Because sensitivity can't be a unitless property. Sensitivity has to be a unit, has to have a unit, right? Yes, as the percentage per daily C. Okay, others? Maybe others can try to answer as well. So what will be the unit in this case? Yes, it will be ohm per degree centigrade, because in case of output it was ohms or resistance, and in case of input it was in degrees C. Okay, so now we'll move towards some, yeah, so let's see. So in this case, what I forgot to mention previously, why is it important to calculate the response time and recovery time? What's the reason to calculate these things? Can you like mention any specific case where the response time or recovery time will be very much like an important parameter? Without that, the sensor is, you can say the sensor is useless or something. Any real life case where you can think of this? Any real life case, like if do we use so many kind of a sensor, so many kind of a things. Let's say a camera sensor. What will happen if we take a picture of sunset or something? So it will capture that image, but it will give us a bit late. Like let's say it like we have to wait for 2 minutes to get the picture. It will be fine, right? There won't be any consequences of these kind of a things. So can you think of any kind of a thing where the response time or the recovery time is very much needed? Or if there is any case where the recovery time should be like a huge amount of time, like I need two examples of in case of the first case, the response time should be less and the recovery time should be very less as well. And another case where the response time should be less Although in case of the recovery time, it should be high or at least in the moderate range. Any examples of that? Give me an example of the first one. Any idea? Maybe something related to cars or something. Yeah. Can you explain a bit? Gas sensors. Yes. Um, it's okay. In gas sensors, the response time should be very less. Yes, obviously. But why should the recovery time be very less? If there is, let's say, an outbreak of ammonia gas inside your room, your sensor should tell you that there is a leakage of ammonia gas and you should run away. So, like, it's necessary to have the recovery time very less because, anyways, like, you are not in the room, right? It can like recover after few minutes, like 5 minutes, 10 minutes. It's fine, right? You don't need the sensor right away. So, yeah, airbags is a good one, but can you explain a bit? During the accident, the response time is very much necessary, right? Because with respect to the response time, the airbag will open, right? But why do we need the recovery time? Reduce the impact, reduce the impact of the hit, right? So can you explain the second part, like why the recovery time is needed? You are going on the right track. Others, maybe anyone want to answer? Hmm. No, you were in the right direction. This is not the correct answer, but you were in the right direction. In case of car collisions or something like that. Think about that. The response time is a very like critical parameter in that case. If the car is coming towards you and your car is going towards them, so what will happen that if you are in a Tesla or kind of a like smart car kind of a thing, what will happen, the car will sense that there's a car nearby, and within a few seconds or few nanoseconds or something, the car will respond and it will slow down. That's fine, that's the correct answer. And what about the recovery time? Can there be a second kind of a collision? If there is a car in front of you, your car stops, right, and it recovered, and in again, if there is another car coming and you have to get the response time again, so in that case recovery time will be a like critical parameter. But it is very unlikely that car will hit your car and then again another car will hit your car. So what will happen? It is the recovery of the sensor, not recovery of your car or not recovery of your airbags or something. It is the recovery of your sensor, specific sensor which is working in this kind of a case. Let me maybe explain this. If there is a car in front of your car and you need to in case of a if you are driving like towards some way and there is a car nearby, what will do, you will turn on your horn. But if you are in a smart car or something, you need a sensor which can sense that and give you the response within some few seconds. So if you are about to about to collide with that car, what will do, you will just press the horn that I will hit your car and you may fast up or something like that. Then within few seconds it should recover, because there may be another car or maybe another vehicle, like there can be anything, right? So you need to use that horn within again few seconds. So in those cases, like if you have avoided that collision, there can be another collision nearby. If you have collided already, it won't be in that case. So other than that, there may be many cases in like daily life as well. like um if you can say if you are playing a game on your mobile phone, what will happen, you are using the gyro sensor. The gyro sensor should respond within a few seconds. Otherwise what will happen that if you are dodging something, like if you are playing a train simulator or some kind of a thing, what will happen, you have to dodge an obstacle, but within next second you have to dodge another obstacle. In those cases, in case of phones or like handheld devices, in case of like wearable devices, it's very much necessary to have a very less response time along with a very less recovery time as well. So are there any cases where the response time should be less but recovery time can be high, or it is desirable that the recovery time is a bit higher? I am talking about the second case. Yeah. Others, please try maybe. Like, even if you are wrong, you can try, right? It's done. I'm talking about this. Any case where the response time should be low, that's fine, but the recovery time is like it's expected to be a bit higher, like a slight bit, but like it should be a higher, like within few minutes or something like that. You can think of some mechanical sensors or something like that. Fire sensor. No, but the question is that the response time should be lower. That's fine, but like even if the recovery time is lower or higher, it's fine, right? You don't have any issues with the recovery time that it is higher or it should be lower or something like that. It's not like that. You need the recovery time should be like moderate or something. I am saying a case where the recovery time should be in like in a desirable range, that it should be a bit higher, not too much, but it should be a bit higher, not very low. Maybe you can think of something with the ATMs or banking systems. Others, please try. Like she has already like guessed a one that was not quite accurate, but still she have tried. Any guesses? Yeah. So if we explain that maybe. So what will happen if there is an mechanical gate where we collect our money from, right? So in those cases, what happens that you should want to get the money as fast as possible, right? The response time should be very low, as low as possible. But in cases of this, like there are like many people's what do like in those cases what they do that you have a time of 5 minutes and you don't take the money within that time. So the what does the bank do for that mechanical sensor? The bank gives us like a few minutes of recovery time. So what will happen after 10 minutes, the doors will starts to close, but it will take at least a minute to close the door fully. So the recovery time is a bit higher in this case. So what will happen if you are seeing that the door is getting closed or something like that, you will take your money quickly. So you will have enough time if you if you have failed to take one note from that that gate. So what will happen that you will get enough time to take that note and the door will close afterwards. So this is a case where the response the recovery time should be in a desirable manner, where you get enough time that you will have a, like, what do I say, like a kind of a beacon that you should take the money right away, or it will get like it will like it will get closed, like the gate will get closed or something like that. Okay. And in that case where I maybe have, where was that, in case of offset, no, no, not in case of offset, maybe, yes, in this case, yeah, yeah, just a sec. So in this case, as I was talking about the memory, so like hysteresis is a bad thing, right? Can you think of another case where hysteresis can be used in a better purpose? Like in this case, we were using this transistor as in memory. Are there any other cases where hysteresis can be used for used for a sensor? Like hysteresis is the desirable property of that sensor specifically. Can there be cases? Any idea? My question is that a sensor has hysteresis. How can you explain that? A sensor has hysteresis, which is undesirable, right? But a case where the hysteresis is desirable, other than this case, optical sensor. Yeah. Can you explain that? Try to just explain that. Why did you think that the optical sensor will be a, like a sensor which will desire the hysteresis effect or something? But change based on color solidities, then it could help. Yes, nice answer. Can you elaborate a bit? Good answer actually. Think about the colors maybe. Just wait for a bit, right? You just type the answer. Yeah, when we use to show the temperature change through LED, I'm this. Nice answer actually. So in case of even like thermostats in like classrooms or something, we use thermostats to do what? That we use to retain the value specifically. Like if the temperature of the room is 24 degree, it should retain the value for some time at least to show the exact that value, amount of the value there. Yes, yes, yes. Lighting systems according to day and night. Perfect example actually. Nice. Let's go to there are few numerical problems left. Maybe we can complete that and then we can move back towards this. Yeah. So maybe we have completed number 4, right? Yeah. So there are 4 different sensors which gives output resistance with respect to change in the temperature. These are the value of the sensors, which is the most sensitive sensor and which one has the most offset. Mm. Yes, yes. So what we have already mentioned that to get the offset value of R, we have to get the value at t equals to 0. If we put t equals to 0, r equals to 10 will be for the sensor number 3. So it has the highest offset among all. What about the sensitivity? Yes, this is also correct. We need to get the value of dr/dt, that is the change in output, that is the resistance here, with respect to change in input values. So it is 5, that is dr/dt is 5 for sensor number 4. So this is the most sensitive sensor. Yeah. So it is a table where the output resistance is given with respect to the change in the temperature in case of a thermistor. We need to know the range of the sensor first. What is the range of the sensor? Take at least 2-3 minutes. Others. These others, try it now. Just guess the values or something. Maybe I can give you a hint. So range is the, in case of this, if the curve was like this, range is the working range of the sensor. In which domain the sensor keeps on working. So your answer is not correct exactly. Maybe you can think about the hint. What will be the working region of this sensor? It won't be 25 to 70. Maybe we can check on this. On 25 degree, the value was 60. On 30 degree, the value was 70. Similarly, on 50 degree, the value was 110. On 65 degree, the value was 140. But when we increase the value at 70 degree, there was no change in the value. So is the sensor working in this region or not? Yes, that is the working region. So if we plot this in this case, the value will be like this. The values keeps on changing, but after 65 degrees centigrade, let's take this is 65 degrees centigrade, the values are getting saturated. So this is a dead band actually. So there is no sensitivity here. So the range will be 25 degrees centigrade to 65 degrees centigrade. So can you tell me the values of dead bands? Where are the dead bands located? Yeah, 65 degree to maybe any values, right? We don't know the value. So, but this is not the exact answer I wanted. We know this is the threshold value, right? 25 degrees centigrade. So what will happen within the range of maybe, let's say it is like from 25 0 to 25 degrees centigrade. What will is the value of this sensor? Yes, 65 to 70 degrees centigrade, right? This will be precisely 65 to 70 degrees centigrade, as we don't know that what will be above that, but after that the deadband can continue. Yes, if there is no offset, it should be 0. That's the right answer. So let's take that this value would be 0 right now. It won't be 0, but let's take it as this. Even if it's 0 or not 0, maybe it can be a non-zero value, still there is no sensitivity in this region, right? From 0 to 25 degree, there is no change in the values. So what will happen, this is also a dead band. From 0 degree to 25 degree there is a dead band, that is the first dead band. Whereas for the 65 to 70 degree region, there is a second dead band. So it has two dead band regions. The first one, it started after this dead band region, that is from 0 degree to 25 degree. It needs at least 25 degrees centigrades to start operating. The sensor needs at least 25 degrees centigrade. Before that, the sensor won't start even. So right now, let's say that this is the value of these sensors, right? So if the sensor equation is mt plus c, what will be the value of m? That can be sensed as the sensitivity. And what is the value of c? That is the offset value, right? Because dr dt should be the sensitivity, that is m, and r at t equals to 0 is c. So that is the offset value. What will be the value of these things? So by this thing we can calculate the offset from here. So we can say that it may be a zero value or it may not be a zero value. It can be a non-zero value as well. So what will be the value of offset? T0 r equals to 0. Okay. No, you are asking me a question, right? At T0 r equals to 0. We don't know that because we have to calculate all the values in this region only from 25 degrees centigrade. If let's say if the curve is like this, we don't know, right? So from 25 degrees centigrade to 70 degrees centigrade, we have the value. So within this region, that is within this working range, what we have already defined, that was 25 degree to 65 degrees centigrade, right? So within this working region, maybe the next values can be like this. Within this working region, we need to determine the value of the offset value and also the sensitivity value. Maybe you can think of like this, like what is the other way to define sensitivity? Up until now, we have already done it. Other than dr/dt, what can be like this? Let me go to the previous slide maybe. Other than dr/dt, we have used this as well. Just other than this dr/dt value, right? We have already used this as well. Change in output with respect to change in input. Maybe we can use that as well. We could write it as m equals to 2 and c equals to 10. Okay. Okay. Why m equals to 2? From the first two values or from what? 2.4. 60 by 25. Okay. So what you are doing that you are calculating by this, right? 60 by 25. So it should be like 2.4. So how come it's like you are saying it 2? Why m should be 2? M can be also in like decimals as well, right? We can say it as 2.4. Why not? Like, why are we saying it as 2? No, it's not needed actually. It can be in like decimals as well. In like real life sensors, it can be like this, like 17.1 or something like that. So it's fine. Maybe you can explain why C equals to 10, you are saying. Why C equals to 10? Yes, correct. If we are thinking of this as a straight line because it is anyways R equals to mt plus C, we can write it as like this, mx plus C. So if C is the offset value, C should be 10 if m equals to 2. But why m equals to 2? Then if m is 2.4, then we have to put the value there, right? 2.4 into x plus C. Yes, if m equals to 2.4, then c will be 0. But is that in all of the cases? In the first case, it's fine. 2.4 into 25, that will be 0. So 2.4 into 30, it is not equals to 70, right? So there should be a c. You like we can't check the only the first value, right? In this case, if we are checking like this value, it's 72, right? Then c will be minus 2. It is not an like feasible number, right? We can't get a resistance of minus 2, negative resistance. So our m is an incorrect number. How to get m? Let's take another 2-3 minutes maybe. Then I will explain this. Or maybe I can simplify a bit. The value was change in output with respect to change in input, not this. Hmm, I got that. That's why I was asking. We need to change in the value of output. So if we take this case, so it should be 70 minus 60 divided by 30 minus 25. It is nothing but 10 by 5. In another case, if we are taking another case, so let's take this one maybe from this 110 minus 100, there's a change of 50 minus 45. It's exactly same, right? 10 by 5. So the value of m is nothing but 2, and by that thing value of c is 10. If you just put that directly, you get the value of c as 10. So the value would be m equals to 2 and c equals to 10, but we need to have the change in the output value divided by change in the input value. That's why not only like if we get this kind of equation, we just what we do that dr dt, that's it. The change in the output by changing the input. It is also another important thing to like remember. You need to have this in your idea. So like in this kind of a case, like where you have a table of this kind of thing, so you get the value of m equals to 2 and then you can get the value of c. So this is it from my side. If anyone have any kind of a questions, maybe you can ask, like from today's class. There were a few questions, and these things are basic. There were many parameters: response time, recovery time, noise, excitations, resolution, stability, deadband, selectivity, repeatability, hysteresis, linearity, range, offset, threshold. This. If anyone have any question, you can ask. Okay. Maybe I can remove this. So maybe we can end this session today. Next day we'll learn more about these parameters. We will have some more maybe mathematical problems, and then we'll move towards further topics. We first need to learn what is these parameters, and why do we need to characterize our sensors in this kind of a parameters as well. Like what is the meaning of these parameters in a real case if we have a data sheet of a specific sensor or maybe an IC. So like in specific to our application, which parameters are the most important parameters, and if we have just wait a second, if we have a desired like IC, like we have, if we have an IC of gas sensors, which one is perfect for our use case, it is the most important thing to learn. How a design gas or any other sensor can selectively sense the mixture of sensors. Yeah, okay. So maybe mm, so in most of the cases what happens, if we have an, let's say maybe I will write it here. So if we have a sensor that is R1 and if we have a sensor that is R2, so there can be specific cases where a sensor selectively chooses ammonia, and there can be specific cases where the sensor selectively chooses N2. But there can be also some cases where the selectivity can be like this. So for ammonia it can be selectivity very high, for nitrogen it can be selectivity of very low, and for hydrogen it doesn't have any kind of a selectivity. So an highly selective sensor is necessary, but not all the cases it gives a very high like sensitivity. There can be an what can I say, like if like in case of like I will maybe explain it like that. We have an enzyme that is called glucose oxidase for glucose sensing. Whenever we are trying to sense the glucose, we have a specific thing that is glucose oxidase. So similar to that, there are several materials that can sense. Yeah. So in similar cases, like if there are several materials which can sense only ammonia, so there can be sensors which have the capability of sensing two kind of gases. Like if we need to sense nitrogen and ammonia at the same time, what will happen, there will be a mixture of those things, and with the reactions happening with the ammonia and nitrogen, a specific gas sensor can sense also the value of ammonia and also N2. But in most of the cases these are kind of like costly sensors. So what we do, there are specific sensors as well, like R1 will work for ammonia and R2 will work for, wait a second, R2 will work for nitrogen. So we use the array of those kind of a gas sensors, where we use both of the sensors in an assembly, and we can sense both of the gases in a same kind of thing, mixture of different gases. Maybe can you turn on your mic and can explain? Mixture of different gases. So you are saying that there is a mixture of gas and we have to select a single gas out of it, right? Or you are saying that there is like a mixture of multiple gases and you have to select only one or two. Maybe you can turn on the mic or you can write it in the chat box.
Hello.
Yeah.
Okay. My question is, if we having the mixture of different pesticide, for example, we are taking the sample of the, in case of it is a liquid sample or a solid sample, whatever it is, we are taking the
Just wait a second, right? My mic is
so
just
whatever it is, the solid state sensor. Hmm.
you
Yes.
can you repeat your question, because like my
Ah,
PC was malfunctioning a bit. Yeah.
okay, okay. Now my question is, if I am having a sample which
Hmm.
contains many analytes, like yeah, for example, pesticide
Hmm.
analytes, pesticide. Okay, for example, I'm taking the fiber optic sensor or else
Yes.
the some any other sensors I'm taking.
Hmm.
So whenever I am trying to get the sample of whatever the presence of pesticides or something,
Yes.
so how I can get a response from that? How I can get that?
Yeah, so like what I
Only
was
one.
saying, that if A is a mixture of, let's say, B, C, and D, three different types of
Uh,
solutions or like gases, if you need
uh,
to get the amount of B specifically, you need a specific, you can say a specific material if you are fabricating the device, or you need a specific
okay.
sensor which can sense only B. Most of the
Mm,
sensors, what happens like with low cost sensors, it can sense
mm,
multiple things at once, and
okay.
it can't sense that precise, so you need to
Ah,
go.
yes.
Yeah, so that's the problem there. Most of the low cost sensors can sense two or three things at the same time, and
Yes, yes.
and also it can like it won't give you the exact quality value you need for a research kind of a thing. So what,
Yes.
so you need to choose a material, like in case of that's why I was saying that in case of measuring glucose, you need specifically glucose oxidase. Glucose
Mm,
oxidase binds with the glucose itself, nothing else. So it only gives the amount of glucose in your blood or in your sweat or something like that, but it won't bind with any other thing in the blood, as we know that blood has so many things in it. So that's similar to that. You have to choose the material carefully that only selects those kind of pesticide or those kind of gas, or like specific to that thing. You have to
okay.
maybe do some literature review where like you can see that this kind of a material only reacts with this. Yes, you can't be universally true there. If there is, let's say, ammonia, nitrogen, and hydrogen there, right? So what
Mm,
will happen out of these things? You have to choose a material which will only react with maybe nitrogen, not with ammonia or not with hydrogen. So you have to
okay.
specifically choose a material which will, it can, anyway it can like maybe with maybe sulfur dioxide, it can react with that. But as your as your this mixture doesn't contain sulfur dioxide, you doesn't need to know about this. You just
Mm,
need to know it's not reacting with the other components. You can analyze that that mixture, what kind of a gases are there or what kind of mixtures are there. You can know that, and you have to just literature review that kind of a material that won't react with the other things and will react with the specific thing you need to measure.
okay. Okay. Thank you. Thank you.
Yeah.